So, yes, the MRS. Well, I'm working at CSIC starting Monday. I'm at ETH Zurich today, and tomorrow I'll be driving from Switzerland to Spain. But I thought it was just easier to say CSIC. So, so the MRS, of course, I'm presenting the work of a very big team of experts, and any mistakes in the presentation is their fault, not mine. No. So, thank God we are not recording this. Anyway.
We do.
So, oh,
we do.
Yeah. Oh, can you right now?
Thank God we're gonna edit.
Oh, yes. So, if I'm not mistaken, I'm giving the last talk of all the instruments of the James Webb. So, I took the liberty of including a little summary here. And you know, we can check all boxes, and we are almost done. The IFU of MIRI is right here. Spectroscopy, MIRI, that's where we are. So, I talked about the LRS yesterday. I'll be talking about the medium resolution spectrometer. So, this is a graph of how the MRS works, and the main thing I want you to take from this figure is these two guys here. These are the dichroic and the grating wheels, which I show here. These are the real parts from the MRS. So, through a very fancy and smart design, the optics of the MRS will split the beam. This is with the light coming from James Webb. So, these two wheels will split the beam into 4 beams aiming the different detectors. So we'll have 4 wavelength channels available at the same time in the MRS. So as Nora described a slicer IFU, I will not go into details. I'm just showing a little animation here. Of course, that's not the real field of view of the MRS. It's just for illustration purposes. This is the slicer mirror for the MRS, and this is the input for the slits or for the slices, where we will get all those beautiful spectra to do great science. So, a little summary of the MRS capabilities. I will not read all the table, don't worry, you can go ask for this later when it's in the, well, it will be available for everyone in the web, I guess. So, the main thing here is that we have 4 spectral channels with 3 bands each. Now, I named them 1A, 1B, and 1C, but I think this is all already. Now we are naming them short, medium, and long. So, I'm used to ABC, so excuse me if I use it too much, but but it's the same, A or short, B and medium, C and long. So, if you want to observe with the MRS and cover the full wavelength range, you will need to take 3 observations. Jeff did a great job explaining this yesterday, and I'm afraid I cannot match your explanation, but I will try. So, the wheels illuminate just a certain part of each channel each time. So, if you want to cover the full range, you need to take 3 observations and moving the wheels for each observation. The good thing is if you only care about one line, say somewhere at 5 microns, you will get for free 3 extra bands. The bad news is if you want to cover from 5 to 28.8, you will need to take 3 observations. Now, all channels in the MRS are concentric. Channel 4, which is the red one here, is slightly offset, but not by much, as you can see in this scale. And here we're showing all the slices in the 4 channels. Blue is channel 1, the short wavelengths. Red is the channel 4, red wavelengths. And as you can see, the slice width increases with wavelength. That's so we follow the width of the PSF. And roughly, the width of the slice is the width of the PSF through the whole detector. Of course, there are some variations, but that's the main idea behind these guys varying. So, if you observe with the MRS, the first thing you will see, the first data you will get will look like this, which, well, if you are familiar with IFUs, that's normal. If you're not familiar, like I wasn't when I joined the team, you could be scared. I was like, what am I doing now with these things? There's supposed to be a galaxy or a star somewhere here, right? So, don't worry. We take care of this and we'll give you nice cubes. But in case you have to reanalyze the detector plane, you will get the 4 channels, the information from the 4 channels in 2 feeds images. This is channel 1, channel 2, channel 4, and channel 3. The first thing you can see is channel 4 is less sensitive than the other ones. We are also studying that, and hopefully we'll find a solution, but more on that in the next years. The other thing is the wavelength changes from bottom to top in the first 2 channels and top to bottom in the red wavelengths, and also there are big distortions, spatial distortions, and wavelength distortions. This these guys here, well, these are the fringes, are supposed to trace constant wavelengths, so you see there's some fancy things going there. We have worked on solving that, and now we can produce beautiful cubes. And Jane Morrison is leading the group to create these cubes, and they are doing an amazing job on fancy algorithms, and they are producing incredibly beautiful data. Well, not like this one, but fancier. This is just an image from the PSF. I wanted to show real data from the MRS, so this is one of the PSF images from CV2 data. So you will get the detector images and the cubes. Now, I wanted to show the idea of the baseline pipeline for the MRS. Carl will give a much more detailed and probably much better presentation of this. And the main thing here, I don't want you to read all the boxes. Well, if you want, sure, it's fine, but I will point at the blue things here, and that's the data you will get. So you will, as you can see, you will get plenty of data for one observation. Just for one observation, you will get all these blue boxes here. So the raw data, the data with first corrections like straight line corrected, fringe corrections, of course, bias flat field, all those things. Then a new set with background and some residual effects corrected, and then the cubes, which are down there. So, well, this is for the extended source and the pine source. There will be some difference in the process, but I will not go into that right now. The idea is that you will get cubes for all sorts of combinations we could think of. So if you are doing a mosaic, you will get cubes for each pointing, for each single band. Then we will combine those cubes and produce a mosaic for each band, and then we will combine all cubes and produce a bigger cube with all bands and all pointings. The names are really funny. We started calling them cube, supercube, ubercube, hypercube, things like that. Yes, it's crazy, and I think we are going now for like something fancier, but it gets more clear, like single dither combined cube and names like that. Everything is well documented and very well explained in the documentation. But just so you are familiar, when you start observing with the MRS and you get a huge bunch of data, what you are getting. And of course, we give a 1D spectra of the coordinates that you can select in APT. An aperture spectrum of those coordinates for each cube, and one final big nice spectrum for all pointings and everything combined. Now, if you want to observe with the MRS, I'll show a little bit of things you really will care about. So the PSF, we are diffraction limited for most channels in both directions, across slice and the along slice. For the along slice, we are not diffraction limited for wavelengths shorter than 8 microns, and across the slice, just for subband and SIG, we are not diffraction limited. For the rest, we are diffraction limited, or roughly diffraction limited. This is the resolving power. You will see that these numbers are slightly different than the ones in the pocket guide. This is because we measured this as of 2 weeks ago. We refined them, and Carl, you will get this CDP info, don't worry. So this is an updated version of the figure that has been showed in the past 2 days. Well, the difference are not much, but I think these are a little larger, slightly larger than the ones we already have. Sensitivities, we have heard much about sensitivities, and I'm showing the old graphs, or I guess the official graphs, and we are refining this. Maka showed all the issues of the background. Alistair is working on this, so I'll just include them for completeness, but remember that we are updating these graphs. Last but not least, dithers. So the main thing here is that you will have the 2-point dither and a 4-point dither pattern. Most of us will care probably about the 2-dither pattern, which is just going in the diagonal of each channel and taking the data points as far as we can. Of course, you can tweak around a little bit of the coordinates, and you can choose which one of the diagonals. And the 4-point dither is mainly repeating this 2-point dither pattern. So go to the diagonals, so those 4 points, for instance, and changing the slice and the alpha coordinates. Now, on top of that, you can select any of these 2 patterns to be optimized for each channel. So if you only care about channel 4, you can just select 2-point dither pattern for channel 4, 4-point dither pattern for channel 4, and so on for all channels. And if you choose channel 1, the pattern is optimized for all channels too. Now, there is an extended source pattern also available or in discussion. I'm not so sure about this, which instead of just caring about the alpha and the beta directions, it's some statistic smart way of getting the ideal sampling, but I'm not too sure about this. STIC, I think, is working on that, and I didn't get all details. But I think it will be also available. So you'll have these two guys for the 4 channels and the extended source pattern. Now, before I finish, I wanted to talk about simultaneous observations. Please note that these are not parallel observations that we'll hear in the next talk or later today. These are simultaneous observations. So parallel observations are using using in parallel 2 main instruments of the James Webb. So say MIRI and NIRSPEC, NIRCam and NIRSPEC, whatever. Those are parallels. Simultaneous observations are within one of the instruments. In this case, the MRS within MIRI. So combining the MRS and imager, observing them with them at the same time. So if you are going to observe, say, the nucleus of this galaxy, you can use the imager in parallel at the same time to observe this branch or however it's pointing. Now, why would you want to do that other than getting beautiful images and great data from the imager? First, it's almost for free. It will add like 30 seconds to your overheads. So if you compare with all the overheads we've seen before, that's really, really nothing. But I think this may need to be slightly refined, but it's about that order of magnitude. So, well, you're using James Webb. You got time for James Webb. Add 30 seconds to your observation. You get also imager data. The other thing is, as you can see, the MRS field of view is really small. If you remember the graphs we saw with all the field of views from all instruments, you had all these beautiful squares from all instruments, and everyone said, and here on the top on the right, what looks like the mouse pointer is really the MRS, that little dot over there. So yeah, that's where we are. So if you want to do a mosaic of an extended source, say of the center of the galaxy or a planetary nebulae, whatever, you will really need high accuracy astrometry. So if you're using the MRS only, it may be a little tough to get really high accurate astrometric measurements. Now, if you include the imager, you have a large field of view that, again, you get almost for free, and you can improve your astrometry here. Also, if you are going to revisit your target, say a high-redshift galaxy, I observe it in cycle 1, and then I go back in 3 years, and I want to combine those data, and I got a very low signal to noise, or almost a non-detection. If I want to combine just the MRS observations, it may be a very tricky thing, especially if it's unresolved or really faint. But if you have the imager data with all these, say, stars around here, whatever structure is here, you can use it to refine or to align all your visits to that target and improve your signal to noise. So again, remember, when you want to use the MRS, apply also for the simultaneous observation. I mean, if you want, because you may get them for a very cheap price, and I think they will be really useful. Okay, I'm almost done. So just some final thoughts. I think, if I'm not mistaken, I didn't miss anything. The MRS is the first mid-infrared IFU in space, and I don't know if it will be the only one. I didn't want to include that just in case I don't want to offend anyone. So it's sorry. I did offend someone. Okay, I missed that one. Yes, sorry. Another thing to edit.
It's not me.
Sorry? Far infrared, yes.
Yes.
So glad I included
It's the first one for instruments started with them.
Yes, so I'm safe? I'm safe, okay, yeah.
Safe.
Didn't lose my job, right?
Can I help you with a spectral mapping? So.
Okay, I knew this was tricky, but
You can always find first in something.
okay, I'll change the space for James Webb, okay? So, anyway, sorry, yeah. That one is on me, it's not on the team, that's me to blame. So, it's an extremely well-characterized instrument. It's really complex, there are a lot of effects like straight-line fringes, some leakage, but we really characterize all those effects and we correct them down to a 5% or even 2% or 1% level. So, you shouldn't care about those things because it will give you beautiful, great data. And we have a large team of guys and girls, sorry, people. That's translated from the Spanish, sorry. Large team of people. There was a late dinner yesterday.
I'll help you with the IFS in space, but not this.
Okay. Yeah, thank you. So what I'm trying to say is a great team of experts, really friendly, apparently not me, but they are, the rest are really smart. And please ask us any questions. You have the PHP and the SPY papers, but we are refining those measurements until launch and of course on orbit. So do email us, ask us in conference whenever you find us, because we will be happy to help you improve your observations, help you with any details of the MRS. And we are certain that it will meet all of scientific objectives of James Webb and also your objectives. So I think that's all I wanted to say. Thank you very much.